Hello. In this podcast, we're going to take a look at conservation of energy. First, we're going to define total mechanical energy and explore how objects store energy. Then we're going to move on to the law of conservation of energy, and we're going to see how we can use the conservation of energy to solve many force and motion problems that are too difficult to solve using kinematics and Newton's second law of motion. Let's get started. Total mechanical energy. This is the energy stored in a particle's kinetic, gravitational potential, and elastic potential storage mechanisms. And our equation for that is simply E is equal to K plus U, and we can break U down even further into its gravitational and elastic potentials. So let's look at calculating mechanical energy. Off to the right here, we have a situation where we have a ball that is a height h above the ground, and it's in the gravitational field. We'll assume Earth's gravitational field, and so the ball is going to start with an initial velocity, and it's going to be an initial velocity of 0, and it's going to be dropped and falling. In our specific problem, we're asked to find the total mechanical energy at point B. When the mass of the ball is 5 kilograms, the velocity at point B is 10 meters per second, and the total or starting height was 10 meters, and at point B, the ball has fallen 5 meters. Here's our mechanical energy equation. Now we have to take the K and the U and break it into more specific formulas that we can use to calculate the actual amounts. So for kinetic, it's equal to 1/2 the mass of the object times the object's velocity squared. And the gravitational potential energy is the mass times the strength of the gravitational field times the distance above or below the reference point. And in this case, we made the ground the 0 reference point. Notice we do not have any elastic potential energy. Well, we go ahead and plug in our numbers, and we find that at point B, the ball has 495 joules of total mechanical energy. Let's move on and talk about the conservation of mechanical energy. Here's our equation. If energy is conserved, then the initial energy in the particle or object is going to be equal to the final energy in the particle or object. And of course, we can break that down into the components of the kinetic storage mechanism and the two potential storage mechanisms. So the system's mechanical energy is conserved when there are only internal conservative forces acting on an object. So this equation is true when only internal conservative forces are acting on an object. So an example of this would be something falling in a gravitational field, provided we make the gravitational field part of the system, and we ignore air resistance or drag, which of course out beyond our atmosphere is a completely accurate assumption. Systems mechanical energy is not conserved when there are internal non-conservative forces or any external force acting on the system. So if you have friction or drag within the system, you are not going to conserve mechanical energy. And it doesn't matter what the force is. If it's an external force, even if it's a conservative external force, you're not going to conserve energy because those external forces are either going to be flowing energy into or out of the object they're exerting the force on. Let's talk about changes in mechanical energy. If you have an external conservative force, the change in mechanical energy is going to be equal to the work plus the change in kinetic energy plus the change in potential energy. When we have non-conservative forces, the change in energy equation looks similar, but there are some differences. First, we can see that instead of work, we have the net work. And also, I want to talk about, even though we have delta K and delta U here, they're not the same when we have non-conservative forces. And let's talk about that. If the non-conservative force is internal, some of the energy flowing between the kinetic and potential storage mechanisms is going to be dissipated and lost. If the non-conservative force is external, then some energy transferred between the system and its surroundings is dissipated instead of flowing into the kinetic. With non-conservative forces, our change in mechanical energy is not going to be the same. Let's solve some problems. First, we're going to look at the conservation of energy when we have a conservative force. Here's a problem. We have a single constant force acting on a 4 kilogram particle, it's asking us to calculate the work done by this force if the particle moves from the origin to a position specified by this vector. Does the result depend on the path? We need to explain that. Part B, what is the speed of the particle at position R if its speed at the origin was 4 meters per second? And finally, what is the change in its potential energy? We're going to assume that the system includes both the particle exerting the force and the particle receiving the force. That way we can count the potential energy as being within the system, and that makes answering problem C a little easier, a little more straightforward. First thing we need to notice in calculating part A is that the direction of the force is not parallel to the direction of the displacement vector. So we need to use our cosine theta formula. So work is equal to the magnitude of the force vector times the magnitude of the displacement vector times the cosine of theta, where theta is the angle measured from the displacement vector counterclockwise to the force vector. The beauty of unit vector notation is that we can break this work into the work done by the x component of the force against the x component of the displacement and the y component of the force and the y component of the displacement vector, and then we can just add them up to get the total work. So again, in the x-axis dimension, the work done is the x component of the force times the x component of the displacement times cosine 0, because both of these are in the same positive direction in the x dimension. Now when we get to the y dimension, the y component of the force is 5 newtons. The y component of the displacement is negative 3 meters. So we put the magnitude in as 3 meters, but because it's in the opposite direction of the force, we're going to have 180 degrees separation in the vectors. That gives us a theta of 180. And of course, when we do the math, we get a negative 15 joules. And when we add the two components up to get the total work performed, we see that it's negative 9 joules. That means that 9 joules of energy is flowing out of the particle that's moving. We were asked if this result depended on the path, and it does not, because this is a constant force, so it makes it a conservative force. It's not changing directions, like a friction force might change directions as the particle moves. So this is a conservative force. Now on to B. What's the speed of the particle at R? Well, our kinetic energy is going to be changed by the amount of work that this force performs. We need to find the final kinetic energy in order to find the final velocity. So we go ahead and take this equation and we find that the final kinetic energy is equal to the work plus the initial kinetic energy. We found the work done in part A. We know from the problem definition that the initial velocity was 4 meters per second, so we can use this equation to find the initial kinetic energy. We find out that the final kinetic energy is 23.0 joules. We can put that into our kinetic energy equation and we come up with a final velocity at position R of 3.39 meters per second. Finally, we're asked to find the change in potential energy. Well, because we made the force part of the system and because the force is conservative, we have an internal conservative force, and we know in that case energy is conserved. So the change in potential energy is just equal to negative the change in the kinetic energy. So we know that the potential energy gain of 9 joules. So the system gained 9 joules of potential energy. Now we're going to look at a problem involving non-conservative forces. Here we have a modified Atwood machine. We have a hanging mass that's going to drag this block along a table, and there is going to be friction involved, so we're dealing with a non-conservative force. So the coefficient of friction between the 3 kilogram mass and the surface is 0.4. The system starts from rest. What is the speed of the 5 kilogram mass when it has fallen 1.5 meters? So the friction is here between the block and the table, and we're asked to find the speed of the hanging mass. We want to treat the friction force as a external and the gravity force as internal. The reason we want to do that is that it allows us to set up an equation where work is performed by friction, and that's going to be equal to the change in the system's kinetic energy and potential energy. Let's take a look at our setup here. This left-hand side is the equation for work. We know that the friction and displacement vectors are in the opposite direction, so it's going to be cosine of 180 degrees. This is the displacement, 1.5 meters, because we know that if this ball is falling 1.5 meters, this block is moving 1.5 meters to the right. The friction force is going to be the coefficient of friction times the normal force. Moving on to the right-hand side of the equation, this first term is our change in kinetic energy, and we have to include both masses because the system includes both masses. We have the final velocity minus the initial velocity squared, and of course the initial velocity will be 0. This last term is our change in potential energy. Notice I'm only dealing with mass 2 because mass 1 is moving horizontally, so there is no change in its potential energy. But there is a change in the potential energy of the hanging mass because it's moving closer to the center of the gravitational field. So we go ahead and rearrange this equation, solving for V sub f. That takes a little bit of algebra. We go ahead and plug in our numbers, and we wind up with a final velocity after the ball has fallen 1.5 meters of 3.74 meters per second. Let's take what we've learned in this podcast, put it all together, and look at a rather complex problem. We have a 10 kilogram block. It's initially 3 meters above the ground. It's going to slide down this surface, and this surface is frictionless except for this 6-meter patch between B and C. Then as it gains speed, comes down this surface, it's going to slow down a little bit because of friction, but it's going to hit this spring with velocity, and as it slows down and briefly comes to a rest, at the point it's briefly at a rest, this spring is compressed 0.3 of a meter. And lastly, the spring constant is 2,250 newtons per meter. The question for us is, what is the coefficient of friction for the surface from point B to point C? First, we want to find the initial total mechanical energy at this position up here, position A. And we know from our total mechanical energy equation, it's kinetic plus potential. However, it's not moving and the spring's not compressed, so we only have gravitational potential. At the top of the ramp, the block's total mechanical energy is 394 joules. Second step, we need to find the final total mechanical energy of the block when it has compressed the spring and has come to a rest. This is our total mechanical energy equation. However, because the block is at a rest, there is no kinetic energy, and because it's at ground level, which is our 0 reference point, it has no gravitational potential energy. It only has elastic potential energy. And so the elastic potential energy is 101.25 joules. Now, we know if we didn't have this non-conservative force of friction, we know that total mechanical energy would be conserved, but it's not conserved because energy is dissipated over this patch of the displacement. So we know that the change in total mechanical energy is the work performed by the friction, and we also call that the energy dissipated. We can go ahead and take our energy equation and rearrange it to find the coefficient of friction, because our change in energy is going to be equal to the work performed by the friction force. Well, that's going to be negative the friction force times the displacement. That is going to be negative the coefficient of friction times the normal force times the displacement. We just go ahead and rearrange that to find the coefficient of friction. We plug in our numbers and we find that the coefficient of friction is 0.328. This is a great problem to end with because it incorporates most of the concepts that we've learned in this podcast about mechanical energy and its conservation. This ends the podcast. I hope you found it helpful in understanding total mechanical energy, when it's conserved and when it isn't conserved. Have a good day.